Hi, my name is Matthew Berg and I'm researching electroluminescent cooling. The modern day lifestyle has become increasingly dependent upon both power generation and refrigeration. This has motivated researchers to try and improve upon the current technology in these areas. My research focuses on using radiation to cool an object. As seen here, we're dealing with two parallel plates separated by a vacuum gap. The goal is to cool the top plate, and since this system only involves two objects, the bottom plate will be heated as a result. I also want to make it clear that we want to be able to cool the top plate regardless of whether it's hotter than or colder than the bottom plate. Furthermore, because the two objects aren't touching each other, they can only exchange heat with each other via radiation. This means that to cool the top plate, we're going to have to manipulate the radiation exchange between the plates. To do this, we're going to use two methods. The first is electroluminescence, which is a phenomenon that occurs when an electrical bias is applied to a doped semiconductor. If a positive bias is applied, the semiconductor will emit more radiation than it normally would at its current temperature. If a negative bias is applied, it will emit less. The second method is near-field radiation. When radiation covers large distances when traveling between objects, it's referred to as far-field radiation, and the radiation exchange is bounded by the blackbody limit. However, when two objects are extremely close together, the radiation exchange between them can actually exceed the blackbody limit. This is known as near-field radiation, and it occurs when the distance between objects is less than the characteristic wavelength of the radiation. This scenario leads to photon tunneling, which allows the blackbody limit to potentially be exceeded. To implement electroluminescence and achieve cooling, I used the theoretical device setup shown here. Both plates are made from a P and an N-doped layer of indium arsenide. The top plate, which we want to cool, has a positive bias applied to it, and the bottom plate has a negative bias applied to it. To implement near-field radiation and enhance the cooling effect, the two plates are separated by a near-field regime vacuum gap. My primary focus this semester was on performing theoretical calculations for the case where the temperature of both plates is 300 Kelvin. To do this, I varied the magnitudes of the biases and calculated the corresponding values for the net cooling power and the cooling coefficient of performance, which is often abbreviated as cooling COP. A cooling COP greater than 0 indicates that the amount of cooling power being generated is greater than the amount of power being used to apply the biases. My theoretical calculations resulted in these figures, which have a few key takeaways. First, since we can generate a net cooling effect, it is in fact possible to achieve cooling while applying a bias to both objects. This is an important finding because previous research has focused on applying a bias to only one object. Second, the positive bias has a greater impact on the magnitude of the net cooling power than the negative bias does. Third, there is a trade-off between the net cooling power and the cooling COP. Larger net cooling powers typically correspond to smaller cooling COPs, and vice versa. In summary, great progress has been made thus far, but more work needs to be done to investigate the cooling effect when the hot object is hotter than or colder than the cold object. I hope you found this presentation interesting, and thank you for listening.